This, these are exercises that are a review about the material on numbers. Remember we discussed some inequalities like this, and we need to go over how we can solve them. Okay, if you have this times this is less than or equal to 0, I think one of the easiest ways to do it is to find where the left side is equal to 0, and then examine the intervals that are determined by those points. Now this is equal to 0 at negative 2/3 and at 3. Now if I look at the closed interval from minus 2/3 up to 3, that works. The things in this interval cause the inequality to be true. For example, if I put in x equal to 0, then I would have negative and positive. So this would be negative. All right? But if x is bigger than 3, then both of these are positive and it won't work. If x is less than minus 2/3, then they would both be negative, and then you get something positive. So this must be the answer right here. Now I can do the same process if I have less than or equal replaced with greater than. And in this case, I find that the intervals that cause the inequality to be true are these two. Okay? All right, so let's look at another kind of a problem where the expression maybe isn't even defined. This expression is not defined when x is 2/3 because you cannot divide by 0. This expression is equal to 0 when x is equal to minus 2. So I would look at these 2 points, 2/3 and negative 2, and I would look at the intervals that are determined by those 2 points. Between negative 2 and 2/3, the inequality holds. See, if you plug in 0, for example, you have negative 1, and that's less than 0. But if x is bigger than 2/3, then the inequality does not hold. Okay, and you can just check that. Put in x equal to 5. You'd have 7 over something positive. This would be positive. And similarly, if x is less than negative 2, it does not hold. And I do not want it, if I plug in x equal to negative 2, I get 0. That doesn't work. So you see, I would have the open interval from minus 2 up to 2/3. Now I have to leave out 2/3 because this is not even defined there. All right, look at this one here. If you complete the square on the bottom, you find that this bottom is always positive. And so the sign of this is determined by the top. And so if you want where it's bigger than or equal to 0, it would just be x bigger than or equal to 4/3. Now let's look at this one here. There's a 1 here. I wish it were a 0. So I will subtract 1 from both sides and say that this is the same as this. Okay? So I need to find values of x where this is bigger than or equal to 0. Now the left side is undefined when x is equal to negative 1, because then you divide by 0. So whatever I end up with, I've got to leave out negative 1. It equals 0 when this expression is 0, and by the quadratic formula that happens at this point or at this point. Now if you take x between these 2 points, the top, namely this, is positive. And of course the bottom is positive as long as you're not at x equal to negative 1. But if x is not between these, the top is negative. Now how do I know that? Well, I know that from high school algebra. This is a parabola which opens down, you see. So what I'll have here is the material between this, which is one of the places where it's 0, and you see I go ahead and include this because I'm allowed to have this expression equal to 0, and it would go from this up to -1, or it could be from -1 up to this other root. Okay? Now here's another problem. I want to find where this is equal to that. Okay, this equality can occur in exactly two ways. Either x plus 1 is equal to 2x minus 3, or x plus 1 is -1 times 2x minus 3, or 3 minus 2x. So you solve these two and you get 4 and 2/3. Let me see, do you get 2/3 here? Yes. I don't know why I have a -2/3 there. Looks like that's wrong. See, if this is equal to this, then you'd have 2 and there'd be 3. Yeah, it's 2/3. Okay. All right. So that would be the solution. There'd be 2 points. And you see it's not very hard to do. I want to solve this one less than 8. Now, how would we do it? This is equal to 8 when either this is 8 or this is -8. So when x is 7/3 or -3. Between these, the inequality works, and off of this, the inequality does not. So that would be the solution right here. And you notice how we do not include the endpoints? That's because I want strict inequality. All right, what are the points on the number line that are further from 3 than 2? Well, those would be the points between 1 and 5. See? All right, I want to show that the absolute value of x is this. If x is positive, then the square root of x squared is just x. This is the positive square root, you see. So it works. If x is negative, then negative x is positive. So if I take the square root of x squared being the positive square root, that's the positive square root of negative x squared, and that's negative x, and that's absolute x. So you see, this is a nice little way of describing the absolute value. It's the positive square root of x squared is equal to the absolute value of x. All right, tell when equality holds in the triangle inequality. All right, here's what happens. In general, you have, instead of an equation here, remember you had the triangle inequality said this. It was smaller than or equal to a plus b. Okay? Now, I think I gave you probably an example. If a is 1 and b is -1, you get 0 here, you get 2 here. What goes wrong, which gives you an inequality, is when these two have different signs. Because when they have different signs, you have cancellation taking place, and you end up with a strict inequality. But if these two have the same sign, so if they're both positive or both negative, then you'll get equality. Okay? All right, so that's the answer to that question. All right, so let's see. Suppose I have this one and I want to solve it. Well, what I could do is I could take this one minus this, minus 8, and that gives me this. And so I would want to find the values of x where that is less than or equal to 0. Now, this can get a little bit fussy. Probably the easiest way to do something like this is to take this expression, have a computer graph it, and then determine where it holds, which isn't too hard. If you do that with this example, you find that this expression is always less than 0. In fact, it's less than or equal to 4. It's less than or equal to 4. All right, I mean less than or equal to -4. Okay, so how do you do this? How's another way to do this? Well, another way you could do this is to use the triangle inequality. This minus this is smaller than this plus this minus this. So now what do? I factored the 2 out of this one, and in place of x plus 2 in absolute value, I put something larger, which is right here, see? All right. And now how's that larger? Well, for the x plus 2, I wrote x minus 2 plus 4, and then I used triangle inequality. Now you see this thing minus that thing is negative absolute x minus 2. And so this expression here is always smaller than or equal to 4. So yeah, it's smaller than or equal to 8. So this is going to be true for every value of x. What about this little inequality here? Well, the left side is equal to 0 at the points 0, 1, and -1. So I look at the intervals that are determined. Well, if I take the interval from 0 to 1, it doesn't work. If I put in 1/2, for example, which is in this interval, I put 1/2 in here, I get negative, positive, and positive. That would be negative. So I've got to leave that out. And I look at the other intervals and eventually find that this should be the answer right here. These are the intervals that work. Now notice how I include endpoints. It's because I have bigger than or equal here, not bigger than. See? Now I want to describe the set of numbers A such that there is no solution to this. All right, I want there to be no solution to this. How can that happen? Well, this is some positive number. Either this positive number is always bigger than 4 for some A, or it is always strictly smaller than 4. Well, the latter cannot take place because you can look at this. If you take x be very, very large, you can make this thing as large as you like. So the only thing we really need to look at is the case where this is always strictly bigger than 4. Now the left side here is this. See, it's x plus 1 plus a minus 1. See, I just rewrote this a little different. And that's x, absolute x plus 1, that's that there, plus x plus 1 minus, and then the quantity 1 minus a, there. And now at this point I'm going to use the triangle inequality and put something that is smaller than this. And that thing is absolute 1 minus a minus absolute x plus 1. And now you see these two cancel, this one and this one. And so I can conclude that if absolute value of 1 minus a is bigger than 4, there will be no solution. Well, what does that mean? It means that a should be further from 1 than 4. Yeah, further from 1 than 4. So you would need to have a bigger than 5 or a less than -3. And as I just pointed out, the other case can't happen, that this is always smaller than 4. So this takes care of the case where it's bigger than 4. And if you have a bigger than 5 or a less than -3, there will be no solution. Okay, so let's look at a little proof here. Suppose that A is smaller than B and they're both positive. I want to show that A inverse is bigger than B inverse. Well, B minus A is bigger than 0 because of this. So if I multiply by A inverse on both sides, I get 0. And on the left, by the distributive law, I have A inverse B minus 1. So that tells me that A inverse B is bigger than 1. And so if I multiply on both sides by B inverse, that will preserve the order because B inverse is positive. And so that gives me A inverse bigger than B inverse. Now here's another one. Show that if absolute x minus 6 is less than 1, then this is less than 7. We do this a lot. We use that triangle inequality, and this expression here is bigger than or equal to this. So you see, if this is less than 1, then this, which is smaller than this, is also less than 1. And therefore absolute x is less than 7. Okay? Suppose x minus 8 in absolute value is less than 2. How large can x minus 5 be? Well, x minus 5 in absolute value is smaller than x minus 8 in absolute value plus absolute value of 3. So what did I do? I wrote this as x minus 8 plus 3. And then I used the triangle inequality. Okay, now if I'm given that this is smaller than 2, then I'd have 2 plus 3, and that's 5. So absolute x minus 5 would be less than 5. All right, here's one of these little epsilon delta things. Obtain a number delta such that if x is closer to 1 than delta, then x squared minus 1 in absolute value is less than 1/10. Well, suppose x minus 1 is less than 1, then absolute x is less than 2. So if this is less than 1, then I can write down this inequality here. And so now if I'm given epsilon, which I will take to be 1/10 in a minute, I would simply let delta be less than the minimum of 1 and epsilon over 3. Then if x minus 1 is less than delta, it follows that this is less than epsilon because I have this smaller than 3 times that. All right? You see, I have this inequality holding because delta is smaller than 1, and I have this less than epsilon because delta is smaller than epsilon over 3, see. Now in our case, epsilon is 1/10, so epsilon over 3 would be 1/30th, and of course that's smaller than 1. So if I let delta be less than 1/30th, this will be true. Okay? Obtain a number delta such that if x is closer to 4 than delta, then square root of x minus 2 in absolute value is less than 1/10. Well, this is not hard. Because as long as x is positive, the square root of x minus 2 in absolute value is less than this. Well, how did I get that? Well, I took the square root of x plus 2 and multiplied by this and divided by it, see? And so that gave me this expression here. Now, obviously, I've got to have x bigger than 0, bigger than or equal to 0, because I can't take the square root of a negative number. But let's assume that we've done that. Then this expression is smaller than this because whatever square root of x is, it's positive. And so things will get bigger if I replace the denominator with something smaller. Now, I can say all of this is so if I have x is closer to 4 than 1, then where will x be? Well, x will be positive for one thing. So if I just let delta be less than 1/5, then if x minus 4 is less than that delta, it will certainly be, x will certainly be positive. This inequality will hold, and I could say that this expression is smaller than 1/5 times 1/2, and that's 1/10. So I did it. Okay, now remember, one of the important theorems was that the rationals are dense in the real numbers. So I'm going to go through an alternative argument. We're going to let these be the integers. See, they're equally spaced. And then we could look at all of the numbers of the form an integer multiple of 1/2, and that would be right here. See, if this is 0, that's still 0. This would be -1 times 1/2, -2 times 1/2, which is just -1, and so forth. See? And then here we would be looking at equally spaced points that have distance between them equal to 1/4. And you could go on doing that. Now, one of the things you can notice is that if you have any positive number, eventually 1 over 2 to the n is less than r for all n large enough. Now, how can I see that? Well, if this is 0 and this is 1, where's a half? It's 1. It's right there. And where's 1 over 2 squared? That's a half of this interval. See it like that? And then half of that would be here. And so you see, I just keep chopping that in half, and I'm getting closer and closer to 0. So we'll go ahead and believe that we can do this and find an n so large that 1 over 2 to the n is less than r. Now, suppose you have a couple of points, x and y, on the number line. Then I could pick n so large that 1 over 2 to the n is smaller than the difference of these. And then I could, you see, these x and y would be somewhere on the number line. So I could look at the bigger of the two, and I could find the smallest value of k such that k times 2 to the minus n is bigger than or equal to y. So see, this could be y right here, say. And then I just pick the one that's closest to it, that's bigger than y, bigger than or equal to y. Then I could consider k minus 1 times 2 to the minus n. This must be smaller than k because this is the smallest one that is bigger than or equal to k. Okay, so now I also claim that it has to be bigger than x. Well, why is that? Well, it's because the distance between this one and this one is 2 to the minus n, which is smaller than the distance between y and x. So I have to have this bigger than x, because if it was smaller than x, the distance between this one and this one would be bigger than y minus x, which I chose it to not be so. So what does that show you? That shows you that in any interval, there is always a rational number, because numbers like this are always rational, aren't they? You have an integer divided by an integer. Now, what I've actually shown here is that special kinds of rational numbers are dense. These numbers are called the dyadic rationals. But as far as we're concerned, the main interest is that the rational numbers are dense. And so we'll stop at this point.